x squared divided by 30 divided by 36 plus y squared over 12 1/4 equals 1.
Okay. Now tilt it right vertical, and yeah, let me zoom in on it here.
Delta x is in 3 divided by 16 inches is my delta x. The scale's in inches. The cross section was, for my cross section, to find the cross section, I subtracted the x squared divided by 36 from 1, multiplied by 12 1/4. Took the square root and then square the whole thing back in terms of pi divided by 2 r squared. To get the cross section being delta x multiplied by pi divided by 2 multiplied by the sum of 12 1/4 minus 12 1/4 x squared over 36 to my y. And the integral from x equals -6 to 6 I found was around 57 inches cubed, approximately 57 3/4, and I found the volume of the model by bringing sum to be 56 3/4 approximately.
Yeah.
So I'm only off by about a cubic inch.
Yeah. You're not doing percent error.
I didn't think of that.
Yeah. Okay. Yeah. That you understand that percent error is a whole lot more meaningful. Clearly, you
Well, I can find that right now if you wish.
No. Well, put it on your paper. I have not been stressing percent error, but I really like it because it does tell you. Okay, Brad.
All right, so I did the curve, or the equation y equals x over 12 divided by, or times the square root of 36 minus x squared, the scale of 1 unit equals 3 centimeters, and square cross sections. And it kind of looks like a bow tie, actually.
Yeah. It's amazing what they come out to look like, and you don't know what they're going to come out to look like until you've done it. It does look just like a bow tie. Yep.
So then the volume model, as given by the lumen sum, was 388.987 centimeters cubed, and then the volume, as given by the volume of solid approximated by integral, is approximately 388.8 centimeters cubed. So it's a discrepancy about 1%.
Okay, great. Okay, Jamie. Yeah. Come a little bit forward here. Yeah. Okay.
I did equilateral triangles, and my equation was x squared plus y squared equals 1. So for the volume of each triangle, I had to use Pythagorean theorem to find the height. And then when I added up all the volumes together, I got 230 inches cubed. And then when I did solve the integral, I got 295 inches cubed. So I had a little bit of discrepancy.
Yeah.
Not really sure why.
Yeah.
But
Now you say you use the Pythagorean theorem to find the height.
right.
Anybody got any observation about that? That sounds wrong to me. Are they? No, they're not equilateral.
Equilateral.
They are equilateral.
Well, you would use the Pythagorean theorem, and your height would become one of the legs.
Okay. I am misinterpreting it. I thought they were isosceles right triangles.
No,
They're equilateral, and therefore, so what? How did you find? What did you actually do to find the altitude?
Find the height? Well,
yeah.
I for each one, I had to do the length of the side squared minus the 1/2 of the base squared, and then do the square root of that, which gave me the height of each one.
Right. Could have done just radical 3 over 2, done it once and for all. But no, that should work nicely. I wonder what the discrepancy is. Is it a matter of scale? Maybe that's
Maybe.
yeah. Okay. Well, good. In any case, where are we? Blythe.
the here.
Yeah, I think that's going to work, yeah, okay. Yeah, tilt it right so it's facing me. There we go. Yeah. Okay, go ahead.
Okay, so I did the equation x squared plus y squared equals 1, and then I did it above and below x-axis.
Mm-hmm.
So I got radical 1 minus x squared and then negative radical 1 minus x squared. And my scale I did 7.5 centimeters equals 1 unit.
Mm.
So the radius was 7.5.
Oh, okay, yeah.
And then so for the equation with the Riemann sum, I got 4,471.9 centimeters cubed. And when I added up all the volumes of it's 2 by 1 rectangle.
2 by 1 rectangles, okay, yeah.
And then I got 4,388.7 centimeters cubed.
Okay,
So it's about 2%.
yeah. Yeah, nice. The accuracy here is it's kind of surprising given given the approximation that it is, and it's quite impressive. Yeah. Okay, Mr. Pierce.
I did x equals y squared, or y equals plus or minus radical x, and I used 2 by 1 rectangles for my approximation. And with the Riemann sum, I got the volume is 562.5 centimeters cubed, and with my approximation, I was a little over. As you can probably see, it goes past the lines.
Yeah, sure.
Some
Yeah.
of the measurements aren't exactly correct, but
Yeah.
they came out to about 652.3.
Okay, and yeah, that's inevitable the way you make your model, and you observe that it should be more because it's a little bit large. Yeah, very nice. Alex.
I did y equals cosine of x. Is this okay?
Yeah.
Okay. Using equilateral triangles from negative pi to pi. And for the volume approximated by the model, I got 69.69 centimeters cubed.
Mm-hmm.
And the actual was 75.81 centimeters cubed.
Mm-hmm.
So I think it's about 8% discrepancy.
Okay, and as you look at it, you can see that you're not going quite out to the edge, so that looks as if that's a reasonable error for what you've done. Okay, great. And last but not least, that makes me nervous to say that because that means somebody is least, and I don't want to think of it in those terms. Let me back up here a little bit.
Alright, I
Okay.
have y equals 2 times the radical sine of x,
Okay.
which I approximated with equilateral triangles.
Mm-hmm.
And important to say from 0 to pi, it goes on forever.
It would, and just as Michael didn't go to infinity, neither did you, and we didn't have room to accommodate that. Very good.
I determined my delta x
Mhm.
by measuring the width of an individual slice
Mhm.
and then filling it as much as possible, which turned out to be about 3/16 of an inch. And
Yeah.
that comes out on this scale to be 30th of pi over 30.
Mm-hmm.
And then my height was found. I took I plugged the equation in my calculator, found the side
Yeah.
in terms of pi, and then the height I found by putting radical 3 over 2 times the
You
side length.
use the formula. Very nice. Yeah.
And I don't
It-
quite have my volumes.
You don't have your volumes, so you're not quite done.
No.
Maybe by the end of the day or something like that?
Yeah.
Okay. Okay, now, the thing that I